Yeah, hello everybody. Um, I think you're not typically the um, people I I talk to. I do research on the physical layer, so this is far many layers too high for me. So I work with NVIDIA. We do research on machine learning, 6G. We experiment a lot with software-defined radios and things like this. And I think the reason why I'm here is because I don't know who has seen a presentation I gave at the 6G at Austin event a couple of months ago, where I spoke about how agentic AI is changing, I would say, research and development in a quite fundamental way. And I had a couple of examples in this talk about how we had agents autonomously implement huge parts of 3GPP specs. And I think that might be relevant for you. And so I think I will just show a couple of examples and then we can have a discussion because I think the research part of what I had in my slides is not interesting at all for you. So I think that I'm going to do unless you tell me otherwise. Okay. Um, so I have one slide that I think might still be relevant, even if you're not doing research. So what I think when you look at the trajectory from 1G to 6G, basically, at the same time as the standards evolved, also the tools we had available for for working on standardization, for validating things, for developing things, and in the 1G and pre-2G systems, basically, there were no computers, and you did it by pen and papers. And I think now we have reached a stage where we're not even doing the programming anymore, but rather orchestrating agents to conduct the research, implementation, and development for us. And I didn't expect that this would go so fast. So basically, we started trying this in December last year. And it has progressed so much that all of the things we thought were 2 or 3 years maybe away, I think we can do much more already today. And I give you a couple of examples, which I considered super impressive a couple of months ago, and now I think everybody would agree. Yeah. Of course you can do this. Okay, so one example. So one of the things I do is I'm a maintainer of an open source library that's called Shona. That's basically used by researchers in the physical layer for link level simulation, system level simulation, but it also includes a ray tracer. And it's all open source. And we have developed this basically as our own internal research tool that we share with the community. And when we started developing this, was all written in TensorFlow because we needed something with automated gradient computation. And so TensorFlow has basically been phased out. And for quite some time, we were thinking about, oh, we should probably migrate this from TensorFlow to PyTorch. And but we didn't do it. And the reason is simply that I would say it's a medium-sized project. It's not super large, but it's medium-sized project, around 60,000 lines of code, I would say. But this is dense code. So this is not like a web server. This is really highly optimized, I would say, signal processing code. So it's not something you can quickly change. And we estimated that if you wanted to migrate this manually, it would take 3 of us 6 months. And so that's why we never did it, because it's not a project, it's not a product. We do this basically in our free time. And so we never did it. And in December, I asked my manager if I could give it a try using agentic tools all alone. So at that time, there was Claude Opus 4.5 just available. And I used Cursor, and I basically migrated Python module by Python module hand by hand. And I could do the entire migration of the code base in around 1 month. And it cost roughly $2,000 on inference cost, which is not too much, honestly. And I would say if I would need to redo this now, it wouldn't even take a week. So I could fully automate this, because at that time, agents, couldn't run for very long tasks like autonomously. So I needed to basically every 15 minutes or so, it stopped and I needed to validate something. we didn't have sandboxes for fully automated agents. So I think now you can do this manually or fully autonomously. And so the reason, but why this is such an easy task, so code migration, basically go from whatever language to whatever language, so easy, because you have the software architecture already given. And it's a verifiable task, and that's really the key. That it means, the migrated version basically needs to pass the same unit tests. It need to generate the same outputs for the same inputs. I can quantify, performance degradations. Does it consume more memory? Is the latency okay? Does it actually even compile? These kind of things. And if you have a verifiable task in software engineering, then you can basically rely on a self-correcting loop where an agent writes code, executes the tests, looks at the output, analyzes the logs, and either says, okay, yeah, I'm done, or it corrects itself. And so that makes it an easy task, and that's why it works so well. On top of this, Shona was easy because it consists of many independent modules with no complex interdependencies, and you can trivialize, you can parallelize this super easily. You can say migrate 10 modules at a time. They don't depend on each other. And on top of this, we got much cleaner code. We could rewrite all code strings and many, basically just say whatever you want on top of this and you get it for free. Okay, but that's nothing related to 3GPP specs. That's really just a software task, software migration task. And I think it's well established now. This works well. There are many companies specializing now in software modernization and these kind of things. And then I tried something which I thought would be more kind of challenging, and that is to implement a channel model from the 3GPP specs from scratch. And so basically, so there's one specification in wireless communications that describes how you can simulate wireless channels, stochastic channel models, and it's a couple of 100 pages filled with tables giving you parameters that seed procedures to generate random numbers, basically. And so what I did is I just downloaded the specs in docx format. So actually docx is actually a nice format because this can be read natively by most agents. So you don't need to convert this to PDF or to Markdown or anything like that. Docx is really good. And especially it preserves the structure of complex tables. So in many cases, in these specs, you have these, it's not even a table, it's I would say tensors where you have, sub columns and sub columns together with sub rows. So these kind of things. And they are very difficult to interpret if you had Markdown or PDF, but in docx that's actually preserved, so that's nice. So I just downloaded these things. What makes the task verifiable is that there are so-called calibration results where I think 10 companies have basically shared the CDFs of metrics that they could extract from these channel models. So basically you have many CDF curves telling you, okay, the eigenvalue distribution of this matrix looks like this, the path loss looks like this and like this. And then you have every company shared their curve, and they don't perfectly overlap, but roughly. And if your channel model, also has a CDF that looks like this, then you can say I've probably implemented it correctly. Okay. And so I also downloaded these Excel files with these CDFs, and then I just gave the task and said, okay, make a Python NumPy implementation of this standard. And that took 48 hours. That time I used Claude Code, so not Cursor, in a sandbox. And 48 hours later, I had a calibrated channel simulator. Not only in Python, but I also asked it to generate an accelerated CUDA version, so that runs on GPUs. And I got that as well. And so that's something which would have taken, I think, us 6 months with 2 people full time. That's a massive task. And so the only area where kind of Claude struggled were these tables because they are really complex. And sometimes, unfortunately, these tables were destroyed in the sense that when they converted from doc to docx, I think some equations got converted to images which are not recovered correctly, and the information is lost. And then another problem is that some of these CDFs you see there, it's not described mathematically what it is. It's not like you have an equation telling you compute this, could compute this metric. It's written in prose, average across a resource block around the carrier or something like this. And then there's a bit of room for interpretation. And what basically then Claude Code did is just generate multiple of these versions and say, under this hypothesis, I get this. Under this hypothesis, I get this. And then I also discovered that there were errors in the CDFs by other companies, basically telling me it's impossible to get this CDF. So I'm sure that they must have used other numbers, pinpointing specifically one entry in a table. And then I looked it up, and indeed, these CDFs were generated for a pre-standardized version. So it basically reversed engineer. Well, this work was super impressive. And then there are a couple of other issues that are not really nicely described, like how to set up, user drops, how you actually set up the whole topology of a network. And I would say that these are not capability limits. These are just lacking machine friendliness. If they would have explained it properly, in with mathematical equations, rather just explaining it in words, there would have been no problem at all. And what I think is the key thing actually to keep in mind here, and I think that might also be relevant for whatever you want to do, if you ever want to do agentic coding to implement stuff from the standard, is that if you have no reference against which you can validate, then it's super difficult for an agent actually to figure out when to stop or when an implementation is considered correct or not. So here in my case, for example, I didn't have a reference implementation, but at least I had these curves, and I could say, okay, whenever you have these curves, then you've implemented it correctly. But if you now think about implementing a standard or a complex protocol, and nobody tells you if it's correct or not, you would basically need to implement the full system and see if it works. And that's a super complex task. So what's really difficult is how do you verify during implementation that what you've implemented is actually correct. So and so motivated by this, we thought, okay, maybe let's get crazy. Could we maybe implement the full 5G specs from scratch? It takes a full 5G standard, and we call this the Project NanoRAN. And so the goal here was, I don't know if I think I've seen in these reference tools that you use also SRS-RAN or I don't know, Okudu or stuff like this. So basically the idea was, can you implement something like SRS-RAN from scratch just based on the specs? And so our setup was as follows. We had basically a computer, DGX Spark, to which we connected a software-defined radio, then connected by cables to a commercial phone. So that's this black thing, that's a Quectel modem. And the goal was to say, okay, build a 5G, base station that lets the UE connect and ping and send a ping. Okay. And so it got access to the full 3GPP TDocs. So that's now, I think, a few thousand pages. We gave it access to Okudu, and also our own with a GPU implementation called Array for lookup. So we said, okay, you are not allowed basically to reuse this code, but if needed, you can use it also for testing. And then we had this run for quite some time, and basically had a loop and saying only stop if you're able to send a ping. And so we had it run for 4 weeks with a couple of interrupts, switching between Opus 4.7 and also codecs. So basically, whenever one of them got stuck, we had the other one take over. So just high-level experience from this. So most of the time is really spent debugging and running the system. So whenever you have something, you need to spin up the whole system, configure the radio front end, this kind of thing that takes a lot of time. So it takes much longer than just compiling a bit of code. It used extensively the existing code as reference. So that's exactly what I said. So without this reference, it would never know if a specific function is implemented correctly or not. So that's why it's a bit of cheating what we do here. And it used a simulating mode from the open air interface. Something also used, you can simulate a base station without actually using all of the software-defined radio. And it used this a lot for debugging and testing. It could use surprisingly all of the hardware commands. So there's an old terminal language called AT to configure the modem that knew all of this. I don't know when the training data this was hidden. And in many cases, it just stopped and it required a bit of human guidance, but actually not much. So I think it totally maybe spent an hour or so reprompting this thing. And so after 4 weeks, we had a working version that could ping it. And mainly it's all written in Python and C. CUDA is not really needed. It connects to the open interface 5G core. And I would say carefully, this is not yet 3GPX to 5G, but you get a fresh implementation of a fully functional 5G base station, which is super educative in the sense, it's super nicely done, very easy, very simple. You can see what's going on. It's very nice. But we are not yet there going totally autonomously from such a complex system to an implementation. So I think without the reference, this would not have worked. And yeah, I can't do such a nice demo now where I connect to terminal because I don't have this setup here sitting. But in principle, I could ping this base station using a phone. That's basically, I think, what might be relevant for you, because now what we actually care about whether we can automate research, but I think that might be out of scope for this meeting. So I would say I stop here, and if you have any questions, I'm happy. You can just have a discussion. I think a lot of the stuff that I'm presenting is already outdated. So I think you can do already much more. I think that has been the story over the last 6 months, that every month we thought, oh, that's the limit, and it actually was never true. And now we literally struggle to find tasks that are sufficiently challenging to be done.